Using the James Webb Space Telescope, scientists have peered back over 13 billion years and found something surprising. Lonely, supermassive, black hole-powered quasars. Now, these ancient cosmic giants aren't where we thought they'd be. They're floating out in sparse, cosmic deserts with few galaxies around to fuel them, raising questions about everything we thought we knew about how black holes and galaxies form. In this video, we will get into the science behind this, why it matters, and what it could mean for our understanding of the early universe. So without further ado, let's get started. Quasars are exceptionally bright objects powered by supermassive black holes, and typically, they form in busy regions crowded with galaxies. In such environments, thick clouds of gas and dust swirl around the black holes, feeding them and helping them grow. However, the Webb Telescope's recent observations challenge this assumption. Using its powerful infrared sensors, Webb took a close look at the regions around 5 early quasars, some of the first ever formed in the universe, between 600 and 700 million years after the Big Bang. It turns out that while some of these quasars were indeed surrounded by dozens of neighboring galaxies, others were shockingly isolated. Imagine one quasar surrounded by almost 50 galaxies, while another has just 2 nearby. These discoveries contradict the idea that supermassive black holes always need dense surroundings to grow quickly. To visualize this, think of the cosmic web, an invisible structure of dark matter that acts like a scaffolding for the universe. According to current models, galaxies, stars, and quasars should form at the densest intersections of this web, where dark matter attracts gas and dust into a kind of cosmic soup. But Webb has revealed that not all quasars follow this pattern. Some are out there in cosmic voids, or empty larders, where it seems impossible for these black holes to have grown so massive without significant nearby resources. Next, let's break down the role of dark matter and the cosmic web in all of this. Dark matter, though invisible and mysterious, is thought to make up about 85% of the universe's total matter and serves as the gravitational glue that binds everything together. It's a vital component of the cosmic web, a massive network where dense intersections are thought to house galaxies and quasars. Essentially, dark matter should be the ultimate delivery service for feeding these early quasars, guiding gas and dust into dense regions where black holes can grow. So, what happens when quasars are found outside these expected dense regions? This discovery forces scientists to consider that some quasars may have formed in areas with less dark matter than previously assumed. Without dark matter pulling in nearby galaxies and gas, these quasars shouldn't have been able to grow as large as they are. Yet Webb has observed supermassive black holes 1 billion times the mass of our Sun sitting in these sparse environments, which raises an exciting new mystery. One theory is that these quasars might have hidden galactic neighbors, obscured by cosmic dust, or positioned beyond Webb's detection range. If true, this would mean that isolated quasars are actually well fed by unseen galaxies cloaked in dust. However, if this isn't the case, it implies that some black holes could be tapping into hidden sources of gas, perhaps in ways we don't yet understand. Such findings suggest that our understanding of dark matter's role in early galaxy and black hole formation may need an overhaul. Additionally, the cosmic web structure and function could be more complex and varied than current models predict. For instance, some areas might be rich in dark matter without fostering a dense buildup of galaxies. By comparing Webb's findings with advanced simulations of the cosmic web, scientists hope to understand where these quasars fit within the Webb's framework. This new perspective may reveal unexpected pathways for matter and energy flow in the early universe, offering insights into how structures evolved in diverse environments. This brings us to the intriguing question. If these quasars aren't getting the steady influx of gas and dust that current models suggest, then how on Earth, or rather, how in the universe, did they grow to such monstrous sizes? One possibility is the idea of direct collapse. In the chaotic conditions shortly after the Big Bang, it's possible that massive clouds of gas could have collapsed directly into black holes, bypassing the usual star formation process. This would allow them to reach massive sizes very quickly. Another theory is that these black holes grew through rapid, sporadic growth spurts, consuming huge bursts of material from surrounding space whenever it became available. Such bursts could explain how black holes in these isolated environments attain such immense masses without constant feeding. Looking at modern observations, scientists have seen other examples of rapid black hole growth that don't fit traditional models. Some recent discoveries involve quasars in sparse regions or galaxies in low-density environments where supermassive black holes are thriving. These cases support the idea that black holes can sometimes grow in isolated settings, reinforcing Webb's findings. Let's also consider the role of dark matter, but in a different light. While traditionally thought to interact only through gravity, some scientists speculate that dark matter might influence the behavior of regular matter in ways we haven't yet discovered. Perhaps dark matter is somehow facilitating material flow toward these lonely quasars, even in areas where visible matter is scarce. This possibility, while speculative, opens exciting avenues for understanding how isolated black holes manage to grow. So, why does all of this matter? For one, it tells us that the early universe was far more diverse and complex than we ever imagined. By revealing that some supermassive black holes could form in isolation, Webb has opened the door to new theories about how galaxies, stars, and black holes develop in environments previously thought to be inhospitable. This discovery could reshape our understanding of the universe's infancy and change how we think about the role of dark matter, energy flows, and cosmic structure. Thank you so much for watching. If you enjoyed learning about the universe's most enigmatic giants, give this video a thumbs up, and don't forget to subscribe for more fascinating space content. Keep your eyes on the stars and stay curious.